this lesson, we will be looking at how to simplify radicals. But to get started, we're first going to take a moment and try to understand what the notation means.
All right, everybody. Today we're going to take a look at radicals. And now to start our discussion of radicals, and our goal specifically today is going to be about simplifying them. First of all, let's introduce what a radical is. So here we go, big old radical like that. Okay, so this whole thing all together, this is what we call a radical. Now, the piece that's underneath that radical symbol there, and actually I'm going to talk about that in a little bit more detail in just a moment, we call that thing underneath there the radicand. Okay? Everything's got to have a name, so there it is. There's its name. Now, usually, there will be a little number that sits right here. We'll call that n for right now. That right there is called our root index, or you'll hear it referred to as the indice of the radical there. And that tells us what kind of root that we're working with. Okay, whether that's a square root or a cube root or fourth root or whatever. Typically, if it's a square root, and we all typically know this at this point here, even if you're not familiar with some of the algebraic operations here, you know that if there's no number written there, it's going to be a square root. Now, a little bit more about this notation, just so that you understand how to use it. And I've watched students make mistakes repeatedly when they start to transition over to using their calculator to do certain things, because they don't actually understand what that notation implies, or the way that notation works. The radical notation consists of two parts. It's this and that. Now that might seem kind of goofy for me to actually write it like that. It seems like I'm needlessly separating those, but actually there are two different symbols here. This is your radical symbol. That little kind of check mark thing, that's what's telling us we're doing a radical, okay, or applying a radical here. This bar, and you might recognize that if I get rid of this here, that looks like the thing that we use when we do dividing, right? We put stuff on top, stuff on the bottom, you know, numerator, denominator, division, fractions. And that is exactly what it is, because that bar actually serves a specific purpose. It implies parentheses. Anytime you see the bar like that, it's implying parentheses either above or below it, or in this case, just below it here. Now, the reason why that's significant is because a lot of our calculators start, when you press the radical button, you will get that symbol and that symbol together. And then you need to remember to close the brackets here, basically to draw that line over top of whatever it is you're taking the square root or cube root of, whatever that is. But you need to remember to close that. Now, sometimes our calculators draw the line, and you simply got to remember to get out from underneath the radical when you're done entering that radical in. But you just got to understand this little bit of a quirk to the notation in order to enter that into the calculator properly. That's the only reason I'm bringing that up. So, most importantly, the whole thing is the radical. This thing underneath there, that's your radicand. And then the number that sits inside that little open area right there, that's your root index, tells you the kind of root you're working with.
Now, before continuing, let's take a moment and talk about what is intended by a radical.
All right, now let's take a quick look at what a radical is. And that might really help with understanding how it works. And to do that, we actually got to take a bit of a step backwards here. Let's take a look at a square. Okay? Now let's say that for my square here, I know that this side is 3 and this side here is 3. So I know, or I can use that information to figure out what the area is. I know that area will be the length of the side multiplied by the length of the other side, the length and the width here. Now in this case, with a square, those are exactly the same thing. Now, yes, that answer in this case is 9, and that's great. But more importantly here, another way of writing that is to write that as 3 squared. Okay? So the square, that little symbol right there, is referring to the area of a square. That's why we call it that. Okay? And we get the area by simply using this number as a factor twice. Okay, and I don't think I'm saying anything particularly profound here. I think most of us get that. If we were to take a look at a cube, let's say, same sort of thing. But this time, let's say that the sides are, well, let's make it 2, 2, and 2. Let's say in this case we're looking for the volume. Now the way the volume works, we know that's length times width times height, so 2 times 2 times 2, which we know is going to be 8. Well, let's take a look at the notation a little bit differently here. With a cube, to get the volume, we take the length of that side there, we multiply it by itself, it becomes a factor 3 times here. We put a 3 right up there. That's the notation that we use. 2 cubed. And we understand that that refers to, or that is, we're finding the volume of a cube. Now it's really important that you catch this, that when we talk about 3 squared, that represents the area of a square where the sides are both 3. When we talk about 2 cubed, we are talking about the volume of a cube with sides of 2. Now, so you understand why I'm saying it like that, so you catch the difference here. I'm not talking about a rectangle here. I'm not talking about some sort of prism, rectangular prism here. These are the perfect square, perfect cube, okay? Now, all that to say, what if the question was a little bit different? Here in the original, I'm asking what's the area? And what I do is I take the length of the 2 sides, and these just happen to be exactly the same because it's a square. I use this notation to produce that number. There we go. Here I'm looking for the volume of a cube. I've got the exact same values on all those sides because it is a cube. That's my notation. 2 cubed gets me the volume. So now let's take a look at what it means when we go the other way. What if I happen to have a square here and I know that its area is 9? Okay, so the area, that's a given to me. Now, question is, how do I go backwards to get the side length? Well, here's where that little bit of notation becomes, important. What we're going to do now is we're going to use that radical symbol to refer to the side length of the square. Okay, so if, let's say I didn't know what this was, and let's use x here, just because it makes for a great unknown. Okay, I don't know what the length of the side is, but I do know that the 2 sides are going to have the same length, so that, okay, I'm going to use the same variable on both sides here. So what we say here is, when I'm looking for the area here, the area is the side length squared. In this case, the side length is going to be the square root of the area. So this is just the exact opposite of squaring, okay? And again, remember, if I don't write anything there, we assume that that's a 2. Now, what does this mean? Well, this notation here is designed to undo what this does. So now bear in mind what this is doing. This is taking that number right there, the base of that power, and it uses that as a factor twice, 3 times 3. Okay, because each side here is 3. In fact, if I told you, maybe this would help here. If I told you that I had a square and the side was length 3, you would know that all of them were 3. So then the question is, if you know that the area of a square is 9, what's the side length? Well, here's how that notation works. We know in this notation that 9 is the same as 3 times 3. So squaring takes that 3, puts 2 of them there. The square root takes 2 of the 3's and spits out a single. Okay? It's doing the opposite of what squaring does. Okay, so again, just to reiterate here, what the squaring does here, 3 squared means 3 times 3. You see that? You put 2 of them there. The square root there says there are 2 in there, I'm going to spit out just the 1. And then that's, as soon as you do that, you don't need to write that symbol anymore. As soon as you write the 2 3's, I don't need to write the square anymore. And this works the same way. Let's say we've got a cube. Okay? And again, I don't know what the sides are, x, 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 but I know that with a cube, all of those sides are the same. Let's say that the area of this cube here is 8. Sorry, area. That was not what I meant to say at all. Volume. Let's say the volume is equal to 8. Well, then I know that the side length is going to be the cube root of that volume. And this is doing the exact opposite of what the cube does. The cube 2 cubed means I'm going to take and put that base as a factor 3 times. The cube root says, inside here I have got 3 of exactly the same factor. And so what the cube root does is it takes that triplet and produces just a single representative. So that this is telling us here that the side length of the cube is actually equal to 2. That's what the radical is doing. Once you understand what that radical notation does, that makes simplifying radicals so much more straightforward.
So now, let's start simplifying radicals.
Okay, so now when we talk about simplifying radicals, what does this actually mean? Well, what it means is this, is that when you're working with nth roots, so we'll even say it like that. So when working, okay, with nth roots, so I mean this could be a square root, cube root, fourth root, or whatever. What we are doing is we are looking for, or we are identifying, and this might seem like a weird word, but I'm actually not making this one up. This is the actual word that we use. We are identifying n tuples of the same prime factors and removing them, and writing a single representative, okay, outside the radical. Now, that might come across as a whole bunch of mathematical blah, 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 until you see an example of what I mean. So let's take a quick look. And all I'm going to do here is just several examples of simplifying radicals. That's it, okay? So let's say, for instance, that I'm talking about the square root of 16, okay? What that means is, I'm looking for, I know that this is the area of a square, or I'm assuming it's the area of a square. I want to know what the side lengths are. Now, there are 2 ways that I could do this, and I'm gonna kind of push you towards a certain method here because I know that it'll work all the time here. But one thing you can do here is you can take a look at this and say, okay, I know that 16 is 4 times 4. I already know that. And I know that what that radical is going to do here is it's going to take that pair of factors, okay, and it's going to give me just a single representative because it's a square root. I'm looking for the area. I'm looking for the side length. The area is 16. I want to know what the side length. The side length must have been 4 because there are 2 equal sides right there. That's one way to do this. Or I could say that the root 16 is equal to, and this is actually what I think is a better method, even though for a lot of really simple radicals, this is actually going to be a little bit more time consuming. But as that number gets more complicated, it turns out this method is actually going to be a little bit, and when I say complicated, I mean like larger. This method is actually going to be a little bit easier. What I'm going to do here is I'm going to take 16, I'm going to break it down into its prime factors. Now, the first possible prime factor is 2. So I'm going to divide 16 by 2 to get 8. I can divide 8 by 2 to get 4. And 4 breaks down into 2 times 2. So here is my list of prime factors of 16. Now I could have written that differently. I could have written that as 2 to the 4. And we might actually talk about that a little bit later here. But for right now, if all we're trying to do right now is kind of get a good handle on what it means to simplify a radical, write them all out like that. And now, my square root is looking for pairs of factors. Well, there's a pair of 2 there, pair of 2's there, which means my radical symbol is going to spit out a 2. Okay, so that refers to an area of 4. The side length must have been 2. This also refers to an area of 4, in which case the side length is also 2. Now, everything's being multiplied here. And when I pull stuff out, everything's being multiplied together, and so 2 times 2 is 4. Okay? Now again, for smaller numbers, this is probably making it harder than it has to be, but it doesn't take long before actually that might be the best way of doing this. Let's take a look at another one. Let's say we're looking at the square root of, let's say 50. Okay? Now, unlike 16, 50 is not a perfect square to begin with. So I can't take this little shortcut right here. So what I'm going to have to do here, at least what I'm going to do, is I'm going to break this apart, 50 apart, into its prime factors. Well, I know that the smallest prime is going to be 2, and I know 50 is divisible by 2, so that's going to be 2 multiplied by 25. Now, the next largest prime is, 25 I should say, is not divisible by 2. It's also not divisible by 3, which is the next largest prime. But it is divisible by the next one, 5. So 25 becomes 5 times 5. Now, I have broken that down into all of its prime factors. So now what I do is I take a look, and I do have a pair of factors right there, 5 times 5. So what that radical notation does is it says, look, that is like the area of a square whose side length is 5, but there's this single 2 that I have here. This is like the area of a square that's got, well, sorry, this is the area of a square, the area of 2. What's its side length? Well, the truth is, I don't know, because I don't have a nice pair. I would need a calculator, some sort of machine to help me figure out what that is. So I only pull out the 5. I can't pull out the 2. The 2 is a single. It's got to stay. And so there we go. Root 50 simplifies down into 5 multiplied by the square root of 2. As soon as you can't grab pairs of factors, I'm done. So let's take a look at another one. Let's say it's something like the square root of 48. Okay? Well, 48, let's see. Again, I want to break this apart into its prime factors. 48 is divisible by 2, that's 24. 24 is divisible by 2, gets me 12. 12 is divisible by 2, gets me 6. And 6 breaks down into 2 times 3. Whoops. Now I'm starting to look for, again, because it's a square root, I'm looking for little squares in here. 2 times 2, there's a square. 2 times 2, there's a square. The 3 isn't paired up, so the 3 has to stay behind. So I pull out 1 2 for that pair, multiplied by, I pull out another 2 for that pair, multiplied by the square root of 3, can't pull that out, it's a single. That's not enough for me to see clearly what the side length would be. So this is going to be 2 times 2 is 4, root 3. That's all we got to do. Now, how do we make this a little bit more complicated? Well, let me ask you for a cube root. So let's say, for example, that we're looking at the cube root of 27. Well, once again, I'm going to be looking for the prime factors. Now, in this case right here, we are considering a volume, okay, as opposed to an area, because we're looking at the cube root here. 27 isn't divisible by 2. It is divisible by 3, though, which gets me 9. And 9 is 3 times 3. In a cube root, I know that to get volume, I need a triplet, okay? A triplet of those sides. So there they are, length, width, height. But I know they're all the same, and so the question is just asking what's the side length of the cube, so the answer is just 3. And because there was nothing left over in the radical, I don't write it anymore. It's done. The answer is just 3. Okay? But let's compare that. For example, let's say that we were asked to come up with the cube root of, let's say, 24. Okay? Well, 24 is divisible by 2, which gets me 12. 12 is divisible by 2, leaves me with 6. 6 is divisible by 2, leaves me 3. Those are all the prime factors. I'm looking for a triplet, okay, to get volume, and there it is right there. So I'm going to pull out a 2, but I'm still left with a single 3 in there, so I've got the cube root of 3 left over, and I can't do anything with that. That is the simplified form of this cube root. Okay, I hope that's starting to make sense there. That's all we're going to do. Now, how do I make this even more difficult? Well, for example, maybe I do something like this. Maybe I take the cube root of, let me just think here. Let's say 162. Okay? Or sorry, not the cube root. Let's make it even more interesting. Let's make it the fourth root. So now, as soon as I start talking about the fourth root, Now, in my mind, what on earth am I talking about? Square root is easy. I'm undoing a squaring, right? I'm going from a area to a side length. Cube rooting, I'm going from a volume to a side length. Fourth rooting, well, I'm not entirely sure what taking something to the fourth power might be. I don't have a physical idea, but I do know that I'm going back to a side length. And so I'm looking for a group of four, a four tuple. Now, once again, let's tear this apart into its prime factors. 162 is divisible by 2. That's going to be 2 times 81. 81 is not divisible by 2, but it is divisible by 3, which gets me 27, which is divisible by 3, which gets me 9, which is divisible by 3, and that gets me a 3. Now, because I'm looking for the fourth root, I am looking for a group of 4 identical factors. Length, width, height, and whatever that fourth one would be. But altogether, that group of 4 gets spit out. I have a representative of that, so the side length would be just 3, multiplied by the fourth root of whatever 2 would have to be, because I couldn't take the 2 out. I couldn't figure out what the side length is that would give me the fourth power of 2, so I leave it like that. And so from there, it should be pretty obvious. I'm talking about 5th root, 6th root, 10th root, what I would have to do. You just lay out your prime factors and start looking for that group of identical prime factors. Okay? Now, what happens if, for example, and I'm going to just throw a couple little twists on here. What happens, for example, if I'm looking for the square root of, or sorry, I should say the cube root. That's where I want to go with this. Let's say the cube root of 72. Okay, well, once again, I'm going to start ripping out prime factors. Because on the face of it, this doesn't look any different, and really the difference is very, very minor, but I don't want you to get confused by anything here. So 72 is divisible by 2, that gets me 36. 36 is divisible by 2, that gets me 18. 18 is divisible by 2, that gets me 9. 9 isn't divisible by 2, but it is divisible by 3, and that gets me 3 times 3. Okay. I'm looking for a cube root. I am looking for a triplet. I have it right there, 2 times 2 times 2. So I know what the side length should be for that. It's got to be just a single 2. I have got 2 3s. Well, because I don't have a triplet, I have to leave both of those inside there. So the very next thing I'm going to do is just multiply those together to get 2 multiplied by the cube root of 9. I'm just going to simplify what's inside that radical. So if you can't pull out a complete group, okay, you just don't. You just leave that there and then multiply those back out. Okay, what else could happen? Well, what else could happen? I could ask you, for example, for the, let's say the fourth root of 32. Here's another thing that might happen. So with the fourth root of 32, again, I'm looking for the prime factors. 32 is divisible by 2. Okay. That is going to get you, what is that, 16, which is divisible by 2, gets you 8, divisible by 2, gets you 4, divisible by 2, gets you 2. Now, what makes this one a little bit different than the ones that we've just done is that it's the same factor showing up over and over again. But that doesn't matter. I'm looking for a group of 4. It doesn't matter that I have an extra 2. In the previous examples, that extra one was a different number, but this one here, it's just another 2 here. So that group of 4 2's becomes a single 2 out front multiplied by the fourth root of 2. I still don't know how to tear this one apart because I don't know how to break that apart into anything smaller there, okay? I'm stuck with my prime factors. Now, hopefully that makes a lot of sense. Just one other little example here. Just so that we've seen it, I would feel bad if we didn't take a look at a question like this. What if the question was, let's say, I don't know, let's come up with, let's say it's the cube root of, let's say, 54, but I put a 5 out front. What happens if there's a number out front? Okay, well, to start off with, nothing, I don't really care about that. I'm going to focus on order of operations. And there's a couple of different reasons why order of operations points to this. But primarily, remember that bar implies a set of brackets around the radicand. I am going to focus on the radicand first. So I'm going to split that up into its prime factors. So 54 is divisible by 2. That gets you 27. And 27, we've already seen just a few questions ago, breaks down into 3 times 3 times 3. Now, that group of 3 3's becomes a single factor of 3 that I pull out, but there's a 5 there. Okay, there's already a number out front, so what do? Well, everything is being multiplied. This is 5 multiplied by the cube root of 54. So when I pull a 3 out, it's going to be 5 multiplied by the cube root of 54, which will be 3 multiplied by the cube root of 2. Now, just multiply the two coefficients together. So 15 multiplied by the cube root of 2. Okay? And that's all you would do if you had something sitting out front. Whatever you pull out of the radical, you are simply going to multiply those together. I hope that makes sense.